Good morning, students. In the last video lecture, we discussed in mathematical physics linear vector space, linearly independent vectors, scalar product, and orthogonal properties. So this is what we discussed in the last class. And very important thing is the quantum mechanics, which we are going to study in the next semester, which will live in linear vector space. So we call this as a Gilbert space. So n-dimension space, abstract space. Another very important rules that we discussed in the last video lecture is about addition and scalar multiplication. So set of vectors and some set of scalars will be there in linear vector space, in which there are two rules. One is the addition and another one is scalar multiplication. Then of course we discussed about the linear independent vectors. So a set of vectors in which the group of vectors that will have linear independent vectors. One vector is cannot be written in terms of another vector is known as linear independent vector. Suppose one vector can be written in terms of another vector, we call this as linear dependent vectors. Then after that, scalar product, which is inner product, we introduced Braun-Ket notation, and we have a line and we have a greater than symbol. Then we call this as Ket vector and Bra vectors. Usually normal vectors, normal wave function or normal vectors will be represented in terms of Ket vectors. If you are going to take the complex conjugate of Ket vector, will give you Bra vectors. So Ket vectors will live in one space, then Bra vectors will live in dual space. So this is what we discussed in the last class. Then another very important property that we discussed in the last video lecture was about orthogonal properties. Kronecker delta function. Orthogonal property means we have two vectors. Suppose if they are perpendicular, the answer will be 0. If they are normalized, the answer will be 1. So together we say about Kronecker delta function. So this is what we discussed. In this class, we are going to learn about Gram Schmidt process, which is very important question as far as this unit is concerned. And of course, we have to use orthogonal property. So we are going to use orthogonal property in Gram Schmidt process. This is a set of linearly independent vectors, and these vectors, suppose if we consider, they are not orthogonal to each other. Suppose we are going to consider some set of vectors. If they are not orthogonal to each other, then we are going to make the process, we are going to make those two vectors orthogonal to each other by means of Gram Schmidt process. That's the idea. Suppose you have two vectors, they are not orthogonal to each other. Okay, you just consider two vectors. They are not orthogonal to each other. Now, we are going to consider that we are going to use this Gram Schmidt process so that those two vectors will become orthogonal vectors. That's all. That's the idea. Okay, we'll have to use, of course, orthogonal properties, those properties and all. Now, where it is used? That question is very important. Usually in atomic physics, we know that electrons will be in the ground state. We know that. Suppose any external perturbation, any external disturbance disturbs atomic system, these electrons will get excited. They will go into many excited states, correct? So we know already about this. These excited states always will have a complex number. So ground state will be always a normal one, normal wave vector. So excited states always will be orthogonal to the ground state. That's the idea. Okay, so why should we study the orthogonal property? It means we know already all wave functions which are there in the ground state will be in the normal state. When they are going into excited states, this will become a complex number, and this will be always orthogonal to the ground state. So your excited states and ground state will be always orthogonal to each other. Any doubt? Will be always orthogonal to each other. Your ground state and excited state will be orthogonal to each other. So we will have to make these things orthogonal to one another That's why we always use this Gram Schmidt process. So this will help all linearly independent vectors which are not orthogonal. Gram Schmidt process will help those vectors should be orthogonal to each other. Not only for two vectors, more than two vectors. Okay. So with this small introduction, we are going to discuss the Gram Schmidt process. Okay. So Gram Schmidt procedure for orthogonalization. So let u1, u2, un be a set of linearly independent vectors. So we are going to consider u1, u2, un be the set of linearly independent vectors which are not orthogonal. So we are going to consider which are not orthogonal, but they are linearly independent. But it is required to obtain another set of orthogonal vectors using this procedure. Okay, we are going to get the help from Gram Schmidt process, and so that those vectors will become orthogonal to the original one. Let W1, W2, Wen, the original set of vectors along the direction. So we are going to consider now W1, W2, W3, they are the original set of vectors along the directions of U1, U2, Un. The procedure due to Gram Schmidt organization is as follows. So we are going to choose W1 which is equal to U1. You just consider this picture first. Okay, we are going to just look at the picture. As I said, U1, U2, U3. Now we are going to consider only real space which contains three vectors. One is U1, U2, U3, something like IJK. Okay, so we are going to consider this as three-dimensional picture. Okay, three-dimension one. So U1, U2, U3, they are not orthogonal to each other. Look at the picture. U1 is in this direction. U2 is here. U3 is here. They are not orthogonal to each other. Right? They are not orthogonal to each other. Now we are going to consider W1 is along U1. As we said, W1, W2, Wn be the original set of vectors along the directions. So your W1 is along U1. Okay, your W2 is along U2 and your W3 is along U3. Okay, now we are going to get the help from Gram Schmidt process in such a way that W1 and W2 they are orthogonal to each other. W3 and W2, W3 and W1 they will be orthogonal to each other. We are going to look into this idea. Okay, the main idea is the projection operator. So we are going to use the projection operator because this will project the U2 vector on U1. I repeat, we have first we will go for W2. Okay, as I said, W1 is along U1. I repeat, W1 is along U1. So W1 equals U1. So choose W1 equals U1. W1 is along U1. So W1 equals U1. The second one is W2 equals U2 dot A21 W1. It means W2 equals U2 minus A21 W1. Here A21 represents the projection operator, projection vector. Projection operator means you are going to project this one on U1. You are going to project this one. Suppose if you have a light here, that will project, the shadow will be there on U1. So this is a projection vector which will project. Now we are going to project only U2 on U1. Okay, you are going to project this one on U1. W2 is somewhere here. The projection vector A21 which is nothing but the part of U2. So U2 dot U1 divided by U1 dot U1. This is a projection vector. What does it mean? Usually we will know that A dot B which is nothing but AB cos theta. It's a scalar product. Actually meaning of A dot B, AB cos theta means B cos theta which falls on A vector. So B cos theta which falls on A vector. So this is called a projection. So projection of B cos theta on A which is nothing but A dot B. So similarly U2 dot U1 means U2 U1 cos theta. Okay, so U2 cos theta falls on U1. So that's why it's termed as projection vector, projection operator. So A21 stands for the projection operator. So part of U2 that will fall on U1 or W1. Okay, then we'll have to subtract with u2. So bigger one is u2. So we'll have to subtract with u2. As I said, part of. Okay, part of. Now w2 which is equal to u2 minus a21 w1, and after having some process, we are going to conclude that w2 will be perpendicular to w1. That's the idea. So this is for the first one. Now we'll go for u3. u3. So as I said, w3. Okay, w3. W3, a part of W3, as I said, that will fall on W2 as well U1, W1. So U1. So that's why it is termed as W3 equals U3 minus, this is A32, which will fall on W2, and A31, this will fall on W1. Okay, is it okay? So similarly, suppose we are going for 4 dimension, U4. So what will happen? This will fall on 3, this will fall on 2, that will fall on 1. So going 6 dimension, everything will go accordingly. Okay, so this is what. Now here W3, we are going to have some process. W3 will be perpendicular to W2, as well W3 will be perpendicular to W1. We are going to consider. This is the idea. Now look at this one, U2 minus A21 W1. So we are going to subtract U2 minus the projection operator multiplied by W1 along U1. Okay, that's the idea. Okay, now the process is like this. So here A21 is a constant, as I said, this is a projection operator, and W2 is orthogonal to W1. So your W2, see, this is your, as I said, this is along W2. Now after the simplification, W2 equals U2 minus A21 W1, this will become, see, perpendicular to W1. See here, this one is perpendicular to W1. Similarly, when you are going for this is perpendicular to W1 and this is perpendicular to W2. See, U1, U2, U3, they are not perpendicular, they are not orthogonal to each other. And we are going to have the ideas of projection vector on U1, on U2, only then we can have the projection vectors of W3, W2, W3, W1, W2 and W1. So this is the idea. Now W1 dot W2 equal to 0. So now they are perpendicular. W1 dot W2 is perpendicular, whereas U1 is not perpendicular to U2. Okay. Now taking the scalar product of W1 and W2 and evaluate to 0. So this is W1 dot W2 equal to 0, evaluate to 0. Now we are going to multiply the equation 2. This is your equation 2. We are going to dot product with W1 on both sides. So take the equation 2 and you are going to dot product with W1 on both sides. So that equation 2 becomes W1 dot W2, which is equal to W1 dot U2 minus A21 is a constant. So I have pulled out. So W1 dot W1. Is it okay? And we have considered already W1 dot W2 is perpendicular to either 0. So this term will become 0. So this term becomes 0 and you will get W1 dot U2 minus A21 W1 dot W1 equal to 0. Okay, this is the term. This is the term. So I can take this term to that side and get A21, which is equal to W1 dot U2 divided by W1 dot W1. Simple idea. So this is the way that we can get the expression for your projection operator, which is equal to W1 dot U2 divided by W1 dot W1. But W1 we have already considered as U1. See, in the first one, W1 is equal to U1. So we can write this as U1 dot U2 divided by U1 dot U1. Okay, U1 dot U2 divided by U1 dot U1. So this is a projection vector. So thus W1, W2 have become orthogonal vectors. We have used of course this one. We will discuss later. Okay. Any doubt? So we have finished one. So now we will go for the second one. W3 falls on W2 as well W1. Okay, we are going to discuss this one. So W3 equals u3 minus a32, so 3 and 2 w2 minus a31 w1. a32 is the projection vector, okay, between 3 and 2. a31 is the projection vector between 3 and 1. Okay, they are all constants determined for the conditions. So now w3 is perpendicular to w1 and w2. Okay, so w3 dot w1 equal to 0, as well w3 dot w2 equals 0. So they are perpendicular to each other. So first we will go with w1 dot w3 equal to 0 for the time being. Okay, for the first one. So we know the equation 5. We know already equation 5. We are going to multiply. This is equation 5. Okay, equation 5. Where is it, equation 5? Yeah, it's here. Equation 5 is here. You are going to dot product with w1. So w1 dot w3, which is equal to w1 dot u3 minus a32 w1 dot w2 minus a31 w1 dot w1. Is it okay? So w1 dot w3 equal to 0. So this equation becomes exactly like this. Any doubt? Okay. Now you just have w2 dot w1. w2 dot w1. According to Kronecker delta function, if I equals j, answer will be 1. Otherwise 0. You see here, this is 2, this is 1. So this term will become 0. This is ij, 1 and 2. This is 1 and 2. So this will become 0 according to Kronecker delta function. So now we will have only this term and this term. So w1 dot u3 minus a31 w1 dot w1 equal to 0. So this gives, you just bring this term to that side. This gives a31 equals w1 dot u3 divided by w1 dot w1. Isn't it? So we have computed now a31. Similarly, we will have to go with a32 now. Okay, the idea is we will have to dot product with w2. So earlier we had a dot product with w1, we could obtain a31. Now we are going to dot product with w2 and you can get a32 and substitute here and get the equation. That's all. So w3 is orthogonal to w2 now. So now take the equation 5. You are going to have the dot product with w2. So this equation 5 becomes w2 dot w3 equals w2 dot u3 minus a32 w2 dot w2 minus a31 w2 dot w1. So the condition for w3 that will be 0. So this will become 0. So this equation becomes exactly like this. Now what is w1 dot w2? 0 according to Kronecker delta function. Okay. So w1 dot w2 becomes 0. You have only these two terms. You bring this term to that side. You will have a32 equals w2 dot u3 divided by w2 dot w2. Okay. So thus we can determine a32, a31 and a21 earlier. Okay. So this is the idea. Now w1, w2, w3 are mutually perpendicular to each other. Okay. So we had a set of linearly independent vectors u1, u2, u3 dot dot dot, you have number of vectors, but you have taken only 3 vectors. This is the 3-dimensional one. And u1, u2, u3 are not perpendicular to each other. They are not orthogonal to each other. But they are related with w1. So w1 equals u1 and w2 is equal to some projection vector. They are related with some projection vector. Similarly, w3 also is related with projection vectors of u3 and u2 and u1. Okay. Now these vectors w1, w2, w3, they are orthogonal to each other. They are related with u1, u2, u3. So this is the idea behind Gram Schmidt process. Is it okay?